Okay, welcome to 10th lecture. So, what we are discussing, let us briefly recapitulate. So, we started with the torsional flexural buckling of column and we have emphasized the role of warping of cross section, open sections, especially inward open section, okay, which the design of which are many times governed by this torsional flexural buckling. So, we have derived the equation for the strain energy. So, strain energy, if you can recall, strain energy contribution was from the two translation U and V as well as the twist, right, and then the twisting degree of freedom, that is the beta twisting angle, that basically was considered while deriving both of the component of torsion. One is St. Venant torsion and another is the warping torsion, right. And then the next step, so since we are following the energy approach, right, we have to derive the potential energy function, right. So, strain energy component we have already derived, okay. I will write down the expression shortly. Then we are working with the expression for the work done. So, expression for the work done, if you can recall that this was the choice of coordinate system x, y and z, right, and here was this column and that was subjected to this load P, right. And then if you can recall, and then the cross section, the way we derive this x and y, we assume that, well, we have this kind of cross section, right, I mean some arbitrary cross section, open cross section, and then we have chosen the origin of the reference coordinate system to be the shear center, and then the CG of this is here. So, the CG has a coordinate x0, y0, right, 0, y0, right, and then along with that there will be two component of displacement, y is u, one is u, another is v along x and y, right, and here there was this, so section went there, and then after that there was this rotation, right, beta, okay, rotation beta, huh? So, from this rotation angle is beta, this angle up to is beta. So, that was complete deformation, right. So, U, V, beta are the three, U, V and beta, okay. U is the translation, deflection due to bending, V is the deflection, okay, and then beta, right. So, then what we have emphasized that because of this beta, U and V will be modified, right, okay, because when we are considering a section, sorry, we consider this is x and this is y, and if we consider a point B, P here, this is point P, on twisting, then if this angle is beta, is taken as beta, then this curve is approximated by the line, and this length is nothing but beta into r, beta into r0, beta into r, okay, or beta into r0 rather, okay, and then I am considering, and then we have seen that we have dropped perpendicular here, and we have also dropped perpendicular on y axis, right. So, if this angle is alpha, then this angle was alpha, this angle is also alpha, and then we have seen that U, V are the pure translational part, right. So, because of beta, the twist beta, U and V will be modified slightly, right. So, U will be modified as U minus y0 into beta, and V bar is V plus x0 beta. How it is happening? Because you see that beta, if you take anticlockwise, right, then positive x direction is here, okay. So, then this is causing a negative component of deformation of point B in the x direction. That is why the deformation in x is basically reduces, right, whether for V it is it is increasing, that is why V plus x0 beta. And how x0 y0 is coming? Because if you take this, see this one is nothing but beta 0 sine beta and sine beta. So, r sine beta is nothing but x y0, right, r sin beta, and from here it is r. So, sorry, r cos beta. R cos beta is nothing but y0, right, and r sin beta is nothing but x0, right. So, that way we have derived, isn't it? Oh, this y0 is coming, the condition that y0 is r sin alpha, r sin alpha, and x0 is r cosine of alpha, if you can recall, right. This angle is alpha, this angle is alpha, this angle is alpha. So, from here to here, I mean beta is very, very less than alpha, right, for any finite alpha, right. So, that is what the component of r sin alpha basically, this is r sin alpha is this one, okay, this is nothing but y0 r cos beta, fine. So, now why we are doing so? Because the vertical deflection, the deflection along z direction, right, the z, that can be obtained by like this, that is d u bar by dz d v bar dz, right, like this. So, integration 0 to L, u bar means here, if you see, so du by dz minus e0 d beta by dz square plus dv by dz plus x0 d beta by dz square dz, right. So, here du dz square plus dv dz square plus minus 2 y0 du dz d beta dz plus 2 x0 dv dz d beta dz plus y0 square d beta dz square x0 square dv x0 square plus y0 square is r0 square, right. So, then r0 square d beta dz, right, integration dz, right, it's fine, okay. So, now we will see that, let us substitute and see. So, what I will do, first I can find out delta. So, we have assumed d is equal to, you have seen that what was the boundary boundary condition that we have assumed that these are kind of restaurant against translation. So, u0 is equal to 0, v0 is equal to 0, u0 v0 at x is equal to 0 and x is equal to L, z is equal to L, z is equal to, right, and then beta is also 0, right, beta is also 0, beta is 0, and then we have also assumed that it is free against warping at the end. So, d2 beta dt2 is equal to 0, right. So, if you can recall, then this was the boundary condition, and also d2u dz2 is 0, d2v dz2 0, d2 beta dz2 0. Why? Because these are coming, then it is rest and bending moment should be 0, right, and then it is not restant against warping. So, and not restant against warping means rest warping moment was what, e lambda d2 beta dz2. So, that must be 0, right. You see, that was the reason why d2 beta d. So, by this you have assumed C1 to be sin yz upon L, v is equal to C2 sin yz upon L, and beta is equal to C3 sin yz upon L. This, you see that, okay. So, now you substitute that, okay, substituting this substituting, substituting. You substitute it there, and then what we are going to obtain is that final expression I am writing. So, the standard integral is coming, and then you will see that the work done will be and then you have to multiply with p. Okay, so then minus y square p by l square 4l square 4l 4l. Here is c1 square, here is c2 square, here is c3 square, r0 square, c1, c3, c2, c3. You see that? So, x0, y0 and r0 is, and you just integrate it and you got these expressions, fine. What is x0, y0, r0? x0 is nothing but cg, the coordinate of the cg, and r0 is the what? Radius of, yeah, so that polar distance, right? Okay, that is the r0, r0 square. In fact, if you integrate over this area, so x0, y0 are the coordinate, and r0 is for the present time we are taking x0 square plus y0 square root. Okay, so that is r0 square, right? And this is also nothing but polar radius of gyration also, right? Isn't it? Anyway, so once we have done that, then what we will do, let us see. Now, this is work done, and strain energy, if you can recall, we have already derived. The strain energy expression was y square upon 4L. This one we have derived C1 square y square EIY by L square plus C2 square y square EIX plus C3 square GG plus pi square omega upon L square, right? X0, Y0 and R0, okay. R0 is nothing but 0 square plus Y0 square. Please recall this symptom. Later I will come then, okay. One second, Please note that capital, capital this omega, capital, omega is nothing but, this is nothing but what? This is the warping constant, right? So, warping constant, and sometimes in literature it is also defined as IW, and for the I section it was what? IF h square by 2, if you can recall. IF is nothing but, moment of area of the flange, right? And h is the depth of the wave basically, right? So, that was okay. So, now we obtain the total, potential energy. So, pi is nothing but what? U minus W, right? So, pi you can write it down whatever the full expression. So, I am going to write it, and through some simplification, some combining the term. That combination I am just explaining to you. Okay, I am removing this two, right? All of you have noted down, right? So, now, so why I am writing in this combination, because you see what I am doing, that the coefficient C1, C2, C2, the coefficients square appearing in square were present both in the work done as well as what in the strain energy expression. So I am just combining the term, okay, and then does it remind you something? It will remind you something, okay. So now how will you solve it? So we'll do energy minimization. So del 2 pi, del C1 is equal to 0 will give one equation, del 2 pi, sorry, del pi del C1 0, del pi del C2 is equal to 0, del pi del C3 is equal to 0. C1, C2, C3. So then if you do when you differentiate, then we are getting 3 expression, okay. You see how we are getting the eigenvalue problem. So what we have started with, this gives the same eigenvalue problem for non-trivial solution. So we are looking for an alternative equilibrium solution. The way we followed the simple system, the same approach we are following. Only thing is that here it is a real system, okay. We started with the flexural buckling. Now we started with the torsional flexural buckling of column, right? So this leads to a homogeneous system which is eigenvalue problem, right? Determinant must be 0, right, for a non-trivial solution, and that's where give the critical load, okay. So when if we write down this determinant, this is so if determinant vanish, then you see that that gives the will get the characteristics equation, okay, and things. Now what we will say, if we are going to see for any for any general case, if x0, y0 and non x0, for any cross section, any arbitrary cross section, arbitrary section, right, x0, y0, r0 are non-zero, right, and then we can get the critical load P. We can get critical P, solve for P, solve P, right, and then that P it can be expressed in terms of Px, Py and Py. So when I am writing here, what is Px, Py, Py? So these roots, you can see that what is Px, what is Py and what is Py. We are writing where whatever we have written there, is pi square E Iy by L square, pi square Ix by L square 1 by R0 square Gj plus pi square G omega by L square. So, you see these are the pure flexural buckling. So, pure flexural with respect to x axis, with respect to y axis, and this is pure torsional, torsional with respect to x, here pure flexural with respect to y. But please note that P cannot be alone Px, Py, P5. It will be a combination for any arbitrary section where x0, y0, r0 is not, then P can be expressed as a combination of Px, Py. This Px pi square EIL by L square, these are all familiar expression to me. This refers to the uncoupled mode basically, the flexure mode, this is also flexure mode, there is y axis, and this is torsional mode. Please note the expression. See, for the Saint Venant one, because it is equivalent to axial force, that's why Gj by R square is coming, okay. And here, pi square E lambda by L square, R0 square is, that gyration, okay. And pi square E lambda, E omega, capital, omega, that is the similar expression to that, flexure, because this is because of the, that warping moment, right? And that's why it's similar. You see that? To that expression. Now we will consider special cases to see what really happens, okay. So special cases when we are considering, special cases. So special cases when we are considering like column with shear center and CG same. That means, that is x0 is equal to y0 is equal to 0, x0, y0 is equal to 0 and r0 0. So, then what happens? Then P is P. So, there will be still 3 root, but P will be minimum of these 3, okay. P will be, so P, then you will get 3 distinct root for P. P will be Px, Py and Pp. So, 3 distinct root, and it will buckle, and one of them will be minimum, one of them will be minimum. So, that means, it will buckle under the one under which the critical load is minimum, right? You see that? Under the value for which, so it will be minimum. So, P will be essentially minimum of this any one, Px, Py and P5. Minimum of this will be P, okay. But most of the I section, hot rolled I sections, especially the one wide flange I sections, it always happens that flexural are the minimum, okay, and it buckles in flexural mode, okay. You see, because it has both the, if they are same, that means it has both axes of symmetry. It has this kind of column has both axes of symmetry, both axes of symmetry. You see that they have both axes of symmetry, x0, y0, okay, both axes of symmetry. So, it will buckle minimum of any of the 3, and in the most of the cases for basically wide flange hot rolled section, the flexural one is the minimum, that is what it buckle, okay. There are other example also, so for that I section, and also you see that for Z section, okay, for Z section, Z is also the shear center and CG are same, okay. So, what is the shear flow diagram for Z section? The shear flow diagram you will see for the Z section, if you consider, from here whatever is coming, whatever will come from here, it will be different, okay. And then from here, so CG and this thing are same, okay, and then it will have the, so torsion, okay, and then there will be I section, the I sections are all, it has both the axis of symmetry, right, I section, And then of course, if you want to consider this rectangular section, what happens is that closed open section rectangular, a closed section, then warping is very negligible. So, warping constant capital omega becomes 0 for this, this for this kind of stuff, capital omega becomes 0, and then this term will not be there. Okay, this is very low warping. Huh? Now, another case where the next case, section, case 2 section. So, case 2, this is case 1, case 2, this is special case 1, case 1, case 2 where the section has one axis of symmetry, So, it has, if one axis of symmetry, that means either x0 or y0 is 0. So, if we consider here, then it will be y0. So, consider that for a channel section, it has one axis of symmetry, channel section, right. So, channel section, so if we consider this to be x and this is to be y, you see that shear center will lie on this axis of symmetry, you see that. So, for here, y0 will be 0. If y0 is 0, then what will happen? So, the equation reduces to, so a characteristic equation, equation reduces to equation reduces to this, So, here you see that. So, one root is of course p is equal to py, and other is a combination of px and p phi, right. Px and p phi are coupled, So, because there is a coupling between it cannot independently buckle with respect to x axis. Okay, what is px? If you can recall, px was what? Px was y square e I x upon L square. So, with respect to x axis, okay, with respect to so so it will under flexile, because it has one axis with respect to axis of symmetry, it can independently buckle. It does not have torsional coupling, but as soon as try to buckle with respect to y, then it will be combined. So, it is torsionally coupled in one way, flexural, and so the flexural buckling with respect to y axis and torsional buckling are coupled, right. So, it will either it can independently buckle with respect to this this axis or a combination, right. So, this is so for channel section one example, and then there are other example. For example, if you want to consider a toy in a hat kind of section, right, hat kind of section, then this is also it is has one axis of symmetry, right. Okay. So, there are other example. Now, in cases if the section has, if a section has no axis of symmetry, if a section does not have any axis of symmetry, then of course it has to be solved in terms of px, py and p phi. It has to be solved, p has to be solved in terms of it will be px, py and p phi. Okay, because then all torsional and all both the flexural mode as well as torsional mode are coupled. Okay, and then minimum you will get whatever is the load by solving this characteristics equation. Okay, so you will say for most of the hot rolled section, okay, for most of the hot rolled section in heavy construction, in structural construction, the torsional mode is not that important, but this really happens for aerospace structure. Okay, so for most hot rolled section, heavy section, heavy construction, especially heavy construction, that's what we encounter in civil, right, construction, Generally torsional uh, torsional mode is not important. Okay, is not not is not governing. Doesn't govern. Okay, govern. No governing. Here the flexural modes are governing. However, for aerospace structure, aerospace, structure, these become important. This kind of, kind of instabilities, static instability is important. Stability is important. Is so these are very common. So for example, aerospace vehicle, what happened? There are this kind of, if you consider fuselage, and then there are, these, fuselage are made of thin, this kind of cell. Of course, these are all stiffened cell, because you can recall that these are all stiffeners will be placed, both the vertical stiffener as well as longitudinal stiffener. But here you see, this is, of course, here, we consider that way, only these sections, it will have one axis of symmetry. But so there, for these kind of things, are torsional flexural buckling are, common. Okay. And that becomes the, predominant design consideration for this. Anyway, so you understand that, for the torsional flexural buckling, I mean, we consider, if you see in civil design, in only one cases that you will find this kind of, I don't know whether you can recall that design of compression member, if you consider only Indian standard code, design of torsional, design against torsional flexural buckling. If you see, if only one angle section is connected, only one side of the gusset plate, single angle section is connected at one side of the gusset plate, then you have to do, check for the torsional, because there will be torsional flexural buckling, and there are some formula given in Indian standard code. Unfortunately, the problem is that that formula is adopted, from some conference paper published by some IIT Madras, fellow, and this is not even validated or verified through experiment done by at the lab. This is for, I was just sharing, when one of the expert was saying, this is for cold forms, sections, they have checked that and they have fitted that model, but that they have put in, in hot roll section steel design for the, I mean, that there is inconsistency. You will not see that formulation in other code. Okay, other code they don't do that way, but nevertheless they, they keep a provision of checking against torsional. Other than that, you will see most of the cases, the way we connect the eye sections, around this gusset plate, we generally don't check for the torsional flexural one. Okay, because they are symmetric, they have either one plane of symmetry or, both plane of symmetry, things like that. You see that? So if you say two eye sections, which are connected back to back, two sides of the gusset plate, that will have one axis of symmetry of the cross section, right? You see, what I am trying to tell you is like this kind of, arrangement. You see that this kind of arrangement. So you will have this gusset plate, in between you have this gusset plate here, both sections. So it has one, you can see that one axis of symmetry. You see that flexural, and that is the load that will govern here, flexural, buckling. Okay, you don't take it. But for aerospace vehicles and aerospace structures, these are very common. Okay. So anyway, so now we have completed torsional flexural buckling. Okay, and we have seen that. So this approach is similar. I don't know whether you are all doing earthquake engineering and you have done structural dynamics, right? So torsionally coupled structure. So you have not, so you will see that for a structure, in earthquake engineering is very important, and there are codal provisions for that, IS 1893, that when you are, a building, you are torsionally asymmetric. Yeah, that means your center of mass is not coincident with the center of rigidity or center of stiffness. Then the, flexural mode and torsional mode are coupled. Okay. So for example, so the same thing. So this here, so there you will see that you consider a building, and then assume that you have a heavy shear wall in these two sides, and then you have much, thinner, things, these shear walls are maybe then you will say whatever is the center of mass and your center of stiffness is towards that. So, you will have this eccentricity, right. So, this is center of stiffness. So, the way here center of shear center is whatever the role is played by shear center and CG, there is the CG and here is the center of stiffness or center of rigidity. Okay. So, then this building become torsionally coupled, and when you get torsionally coupled, then of course, you need to increase the demand by some percentage on the other side. You see that. Okay. And then always in seismic design, you have to consider some minimum eccentricity. Okay. 5% or whatever, right. There are formula in the code, right. 1893. So, because of there are two to take care of the accidental eccentricity. Okay. So, things are similar. So, torsional flexural coupling in building in earthquake engineering, and here also torsional flexural, here it is buckling. Okay. But the special cases are symmetric, one axis of symmetry, two axis of symmetry, and things like that. Okay. So, now what we are going to consider? We are going to consider next is that lateral buckling. Lateral buckling of beam. So, lateral buckling of beam happens. So, we have just concluded torsional flexural buckling of column. Lateral buckling of beam, when it happens, see, if you consider a beam, then the beam is subjected to transverse load, right, and it is bending in the vertical plane. Now, what happened is that the top flange is under compression, and bottom flange under tension. So, tension does not induce any instability, but under compression top flange try to buckle. So, top flange will try to buckle, that means it will go out of plane deflection, bottom flange will remain in its plane. That means there is difference, there will be differential kind of displacement between the two ends, that will lead to, so that must be accompanied by twist. That is why. So, this thing also you consider in design, in steel design, when you design the beam, laterally unrestrained beam, you can recall that that time you have to, and then you have seen that allowable bending stresses reduces significantly depending on the classes of imperfections that you consider, and then slenderness ratio, those are the two prime factors, right. So, that thing we are going to, and we have very complicated formula, especially for the case where there is gradient in the bending moment. So, bending moment is not uniform. If it is pure bending moment, uniform bending moment, then pure bending, then the formula was simple. But if it was there are shear force and then there is gradient in the bending moment diagram, then complicated formula was there, right. We will try to derive the formula which is in steel design code. Okay. For the simple one. Okay, and we will see how it is coming. Okay. So, what is really happening here? You are considering, so here is a, so here is a, beam. Okay, beam section. You see that? Maybe here is the all simply supported. Okay. So, what happened that under transverse load, transverse load, or if there is some bending, okay, then what is happening? That this fellow will remain, the top portion is under compression. You see that? So, these are in compression. So, it is in compression, and then bottom portion is in tension, right. So, under tension the bottom flange is going to destabilize, but under compression the top flange is going to destabilize. So, what is going to happen then? This fellow will remain in its place, but the top one will come out of plane deflection. You see that? This one, and then there will be lateral. So, what is happening? Now, I am going to consider this one is Z maybe, and this axis is Y, and then along this is X axis. So, what I am going to consider is the vertical plane is XZ plane. Okay. Yes, right, and then coordinate system. So, you see what is happening, initially the beam was remaining in equilibrium under vertical load, right. In the bending was essentially happening in XZ plane. The initial bending, so initial bending in XZ plane. Initial bending in xz plane, it was happening, right? Then beyond a critical bending, and for this time we are going to consider that it is subjected to pure bending. That means the uniform bending moment, because that simplifies our case. Okay. So then what is happening? This fellow is going to remain in its place, this flange, but then top flange is coming on the there is lateral bending in the xy plane. Okay. So what is happening? You see that. Well, initial bending is then the section loses stability. Okay. How? The top flange under compression bends laterally, bends laterally, in bends laterally, that means in which? In xy plane, right? Whereas bottom flange under tension, remains in xz plane. Okay, xz plane. So this leads to lateral buckling. Lateral flexural buckling. Okay, lateral flexural torsional buckling. Torsional buckling of the beam. So essentially, what I am going to, when I am going to draw it, in xz plane, what is essentially happening? Yz plane. In yz plane, what essentially is happening? This is y, and this is z. Y, z. Okay. So, so the top flange is going to deflect this fellow. See, of course, there is initial deflection, in Z, but that we are not considering. So, this fellow is going here, so this is the vertical W. Okay, we don't we will, and this is the top flange is maybe V. This is along Z, This is along Z. Sorry, this is along Y. This is along Y, and this is along Z. Okay, this is V. This is the top flange. Top tension, and then this is in compression. And then whatever this is happening from here to here, this we are considering as V. So you understand why this twist is happening. This angle we are defined as beta. Beta is the angle of twist. Angle of twist, and this angle of twist due to differential bending in the flange. Angle of twist due to differential bending in among the flange. flange, differential bending among the flanges, right. T is for tension, C is for compression. Top T is the tension flange, T is for tension flange. Sorry, T is top one is not T, top one is compression, TC, okay, TVC, and this is VT. T is for tension flange and C is for compression flange. So, in the analysis, what we will do? In the analysis, we do not care about the vertical welding. Okay. Why? Because in this analysis, in the stability analysis, we do not care about vertical bending, vertical bending that is in YZ XY plane, in XZ plane. We do not care about the vertical bending in the XZ plane. Why? Because this is, so why, what do we mean by when I say caring? We do not include the potential, we do not include the contribution of strain energy of vertical bending in the analysis, because instability as far as vertical bending is concerned, other than inducing compression and tension in the top and bottom flange, it does not have any other role. In the process of instability, it does not have any other role. So, because in the vertical bending, the beam was under equilibrium on the transverse load, okay, prior to instability buckling, right. So, we are not going to consider its contribution in the strain energy, okay, fine. We are only going to consider the contribution of strain energy for the lateral buckling. So, this is vertical, this is lateral buckling, you see that some bending is happening in the what, XY plane, this is bending in the XY plane, right, XY plane, this is bending in the XY plane. So, in the XY plane when it is happening, let us see what will be the expression for the strain energy. So, what expression for the strain energy, strain energy expression we are going to consider is, of course, the EI, because of lateral bending, that is the bending with respect to which axis? Bending with respect to Z axis, lateral bending is happening. So, EI ZZ by 2 integration 0 to 2 and d2v dz2 square dz, right? Right? Isn't it? G is basically the component for the lateral displacement component, right? And that's what essentially happening. V, you see that. So, this one, it's the and then of course you will have this component which is integration 0 to L Gj, half will be there, Gj d beta by dz square dz, and then in addition to that, what we are going to consider, that is capital E, capital omega d2 beta dz 2 square dz. You see that? This is the flexural, this is the warping, contribution by warping torsion, because it is anyway open section and then I section, right. So, this is because of warping torsion, this is Venen torsion, this is torsion, flexural component, right. So, all of you are wondering that why I am not considering the contribution, contribution for the vertical bending, why I am not considering EI yy d2b dz2 square dz. Because why I am not considering that? Because that has no contribution as far as the losing stability is concerned. The vertical bending doesn't have, the bending in the vertical plane doesn't contribute in the instability process. Of course, is contributing the instability by causing that kind of stress condition which are conducive to instability. Okay, this point you must understand clearly before proceeding. You understand that? Okay, so you when you say that why I am not considering EI, y upon 2 integration 0 to L d2 d2w dz2 square dz. This we are not considering. You see that this we don't require to consider. Okay. Now, so this of course then v beta and v beta and all these things we can assume some expression. This fine. So that's not a problem. We can solve it. Okay. But let us now do for the work done. How the work done is going to come. Okay, because in estimating the potential energy function, we have the strain energy component as well as work done. So we will see that how the work is coming. So what are the external moment here? The work done is going to external forcing. So what I am considering that this beam is subject for simplification. This beam is subjected to pure bending. What does it mean? Pure bending mean this is subjected to end moment and end moment, that is M, and here is M, pure bending. That means M over the span. Bending moment M over the span. Same moment, uniform moment over the span. You see that? Why we are taking that? Because then it will be simplified. Otherwise, it is possible, but otherwise it will be little complicated. So, okay. And here we are considering the Royal. We are not considering the I mean, because torsional flexural buckling we have separately considered. We are considering that this is have both the axes of symmetry. Now you consider the situation why this was so complicated formula in your code when you were considering the laterally unrestrained beam, because that time both the lateral buckling was present as well as torsional flexural buckling was present. So you have to do a lot of calculation for the shear center and etc. etc. Okay, we are having a separate treatment for the lateral buckling of beam, and we have separate treatment for the lateral torsional buckling of column and for the torsional flexural buckling of column. Understand that? Good. So then we are considering that it is subjective to uniform moment. We can consider the distributed load, and so that's not a very big deal. I mean, that's not a big deal, but just for simplification. Okay. Now, if it is subjected to these two, your pure moment M, right? I am considering the end. These are applied. Pure moment is applied. Okay. Pure moment are applied at the end. So this is also M. And this is M, okay, M, and there is no shear force, no shear deformation. Okay, so now how M is going to work? M, there must be some rotation. Yeah, rotation is happening. Why rotation is happening? Yes, you see that. See, so it was remaining vertical and then it is rotating. You see that this rotation, right? It was remain vertical and then it is rotating. You see that. So this angle. So and then I am defining this rotation of this, this section, this one I am defining this angle to be psi, and I am defining this angle to be psi. So what is that psi rotation? Psi rotation is the rotation of the beam section. So rotation with respect to y axis, and then this rotation is happening at the xz plane, right? We have to find out how to find out psi. Psi is the rotation at the end of the beam, and this rotation is happening with respect to y axis and in the xz plane, right? So So, let us keep that expression, okay, and we will come there later, and I am just removing this. So, let us do work done. Huh? So, this psi is the end rotation of the beam. That means with respect to which axis? With respect to y axis in the xz plane, psi. Okay, so work done is 2m psi. Why 2m? Because both the end m, so m into psi both the, so that's where this 2 is coming, 2m psi. Now we have to find out psi. How to find out psi? You see that why this psi is happening? This psi is happening because you see that, look, V I am defining that this deflection of this one, and this deflection of this C, right, this one. So, psi is what? See, psi is nothing but this fellow is Vc, this fellow is Vt, Vc minus Vt divided by h is the length, this length, this is that is the psi, right? That is the angle, huh? This is beta, this is not psi, this is beta twist. Psi is little, you have to visualize a little different way, psi, okay. See what is happening, you see that. See, this beam is subject to going to out of plane deflection, right. So, what is in plane displacement because of out of plane deflection? When it is laterally deflecting in the xz plane, what is the deformation along x? What is the in plane deflection due to out of plane deflection? In plane strain, you integrate von Karman strain, right? If you integrate, this is nothing but d v c by dz square, dz integration 0 to L. I mean, if what is this? Half integration 0 to L del Vc del G del square. I am considering the top fiber which is subjected to Vc, right? What is that Vc? Vc is what? Vc Vj divide. This is what? von Karman strain of the Vc is out of plane deflection, right? Deflection along y, right? Or the top fiber. So, and this is nothing but epsilon out of plane deflection. So, but the strain is axial strain, that means along z, right? This nothing but epsilon z. This is nothing but epsilon z, na? And half of that. So, if I want to consider only one plate, then it is 1 by multiplied by half, because this is contracting in both the end, right. So, this is total half of that. Is that fine? Similarly, in tension, I am also going to write half integration 0 to L d Vt by dz. You understand what I am doing? I am integrating the von Karman nonlinear strain, which are in plane strain due to out of plane deflection. The beam is going through out of plane deflection in the lateral direction along the y, that is Vt. So, I am now considering top fiber and bottom fiber, and then I am for the top and bottom fiber, this is for top compression fiber, this is tensile fiber. So I am integrating the von Karman strain over half of the length. That's why 1/4 because both end. So at the one end, what is the this is the change in length of the compression fiber. This is the change in length in the tension fiber. So essentially, these are nothing but this one and this one. Okay, but I am just okay. Now, so now what is VC? VC nothing but V plus beta into H by 2, V minus beta into H by 2. This you understand from there, right? Right? Now, psi is nothing but delta C delta T divided by H. I am now going to remove everything, this one, okay. I am going to write delta C minus delta T is nothing but So, work done, work done is 2m into psi, then 2m into psi means 2 will cancel out. So, m integration 0 to L dv dz dv dz. That is the work done. So, you find out expression for the strain energy, expression for the work done. Okay. So, then we will be able to find out potential energy, and then we subsequently will discuss. So, please be careful, find try to understand each and every point, how this work done expression is coming, why this psi, the end rotation, how end rotation I am relating with the out of plane deflection V as well as this twisting beta. Okay. This is little tricky, not tricky, but please try to conceptualize it. Okay. Thank you very much for today's class. Okay.